So our very own Mehul Makwana, who is a research associate at Imperial College and who also works as a consultant at the multi-wave company. And so it's all yours now, Mehul. Please go ahead.
Okay, thanks for Bogdan, Sebastian, Muema for organizing this. I guess this may become more of a regular occurrence in this world, at least in the near future. So this is the first time we're doing this. I'll play around with a few of the features, and then just to get a feel of what you guys, I guess, can see and what you can think of it. Webinars are slightly different, I guess, to seminars, so a bit more interactive. So I'll see if I can utilize some of these other options. So I'll start off. Let me see if this works. I'm going to start with a poll question just to know how to pitch this. So let me know if this works. Overview content. Okay. Can you see a poll or not?
Yes.
Yes, we do.
Okay. So I'll be talking about topological edge states, but there's a large swathe of literature out there on these topics. So I just want to get a feel of what people know, how much they know, and just basically, I'll try to give as much of a layman's kind of interpretation of the modes that we've been looking at Imperial. So yeah, yes, no, maybe. Okay, there's 20 people. No one's. Actually, hold on, there's more. It's 23 participants. I've set the poll time to 7 seconds. Okay. So one person said maybe.
That was me, Mehul, who said maybe. Yunus.
Okay. Okay, so it's like you've got a mixed bag here. 6 yes, 8 no, and then 1 maybe, and then 6 decided not to answer. So I'll try to pitch this right down the middle then. So I don't know how much useful that was, but so yeah, I mean, a lot of the concepts that are used can be applied to many different wave systems. As Sebastian said, I work with Imperial and also with multi-wave. Feel free to jump in and ask any questions. So in terms of the content of the talk, I'll provide some motivating examples to begin with. And then the focus of the talk will be on symmetry generated topological modes. So these are reliant upon the periodicity and the type of periodicity that the structure has. Normally, the canonical structures used are based upon graphene, so hexagonal. You could also have them for non-hexagonal structures. I'll talk about general principles that you may wish to follow if you want to generate these states and where and when they'll be useful. Something in the literature is there's a lot of people looking for new physics, but not as much, I guess, bringing everything together to think, okay, how can we put this into a finite number of principles and how can we move it towards something potentially useful? And then I'll talk about applications for these types of states, and then I'll talk about future directions and acknowledgements as well. This work has been done by many people, so they'll be rightfully acknowledged later on. So ultimately, what are we trying to do? We're just trying to come up with a way to make energy go from one area to another in the most efficient means possible. How clear is the screen, by the way? It looks kind of grainy to me, to be honest. Is it okay?
It's very good.
Excellent.
Okay. So ultimately, that's the goal here. What is the most efficient means and simplest means to transmit energy from one place to another? So that's what we'll be looking at. This slide is basically just a pictorial illustration of the results that we have and try to draw the attention of the of you guys, basically. Okay, so topology, what is it? Ultimately, you have these particular structures. For example, if you have a coffee cup and you have a donut, they're classed as being topologically similar. So they have certain quantities that can be defined on them, which are invariant. And these quantities will persist whether you take your coffee cup. So for example, if it's made of Play-Doh or like something soft and you mold it into a donut, that quantity that's defined on it will be invariant, so it will remain constant. An example of that are these structures here. These we classed as manifolds. So G here in this formula will be the genus, and this math cal K is your Gaussian, is your curvature. And for us, when we're dealing with periodic structures, which I hope most of you are familiar with, when we're dealing with 2D structures, which will be the focus of this talk, we have our two-dimensional Brillouin zone. When we have a two-dimensional Brillouin zone, we have a Kx and Ky axis, and the periodicity along the ring of the donut, i.e. along the closed circle, that's, for example, your Kx, and if you go the other circle around, that's your Ky. So by doing this, we make a donut from our Brillouin zone, and that's our closed manifold. And it's upon this for which we will define our own invariants, and these invariants tell us about certain properties that exist on this donut, i.e. our Brillouin zone. So what we'll ultimately be doing, we simply put, we look at degeneracies, and on the right, you have panel C and you have panel D. On panel C, you have highlighted there Dirac cones, highlighted by these red circles. The structure we're looking at is shown in panel A. So what we have is we have a triangle within a hexagon, and this is tessellated in infinite space. And if we rotate that triangle, then we end up breaking those Dirac points or those degeneracies, and we get the band gaps that we see in panel D. So this can be done either by breaking spatial or time reversal symmetry. And the reason why here, I'm going to play around with annotate now. So let's just see. So yeah, the reason why I've highlighted topological and then there's topological with brackets around it is because this one, when you break time reversal symmetry, those are truly topological, because upon the donut that we have, i.e. our Brillouin zone, we can define a topological invariant or quantity that exists for the entirety of the donut. Whilst when we look at these, say, symmetry generated states, such as these, where we have a Dirac cone here, and we rotate, this line is too thick. When we rotate this Dirac cone, for example, or when we rotate this internal triangle, we can break this symmetry. And however, we end up having quantities which are purely defined, in these regions. Let's see. Bear with me. We purely have them defined in and around these valleys here. So they're very local. So they're not defined for the entirety of the manifold. So that's the difference between breaking time reversal symmetry and not breaking time reversal symmetry and using geometry to engineer these states. Okay, so that's exactly what I was illustrating. So you have two types, broken time reversal symmetry and preserving time reversal symmetry. When you break time reversal symmetry, you end up with a single state, which will go in a particular direction. So only go in a particular direction. There's no backwards mode to couple into it. There's nothing going this way, essentially. Here we have both. We have bidirectional states, and this happens when we break spatial symmetry. Okay, so what are examples of broken time reversal systems? So in electronic systems, we would have something similar to the quantum Hall effect, where we'd apply a perpendicular magnetic field to a plane. You'd have electrons which drift off to the side, and then you end up with conducting channels around the edge. In mechanical systems, contrary to this, you end up having gyroscopes. Now, even though this is a good illustration and you're trying to emulate, in a way, the spin of an electron, it's not as pragmatic, let's say. So when it comes to using symmetry-generated states, this is a benefit of them. They are passive, they are simple to design, and they work for classical systems outside of quantum. So what are the benefits? Like, at the end of the day, if we're going to research something, if we're going to espouse, we should be doing this, we should be using this, then it has to be better, or has to at least indicate theoretically that it's better than competing designs. So The example on the left, which was taken from this, which is for acoustics. Here, I don't know how great your screen is, but either you can create a guide which is geometrically engineered, so you have medium 1 and medium 2, and they're engineered via the geometry, or you can remove a channel of scatterers in the middle, which is the bottom row here. And when you remove the bottom row, that's known as a cavity waveguide. And if you introduce some kind of positional disorder, as they have done here, for both systems, what they found is, at least numerically, that the geometrically engineered topological waveguide is superior to the cavity waveguide for certain types of disorders. A natural question to ask is, what kinds of disorders and when? Either you could have positional disorders along a straight waveguide, or as you see on the right, you could have, say, sharp bends. Can the energy go around a sharp bend? And the natural questions to ask is, what is the transmission compared to, say, a straight waveguide? So in this paper for acoustics as well, the red bar that you see here is for the Z waveguide in terms of transmission, and the green is for a straight waveguide. And as you see, they map onto each other quite well. And what this seems to indicate is, at least for this regime and for this range of frequencies, that this Z waveguide is almost as efficient as, say, a straight waveguide. So here you have two different types, it's almost two different types of disorder. Along a straight waveguide, you have positional disorder, i.e. I have a straight waveguide, I mess around with some of the scatterers. These and this one is for sharp bends. I introduce a channel, which is very sharp. You'd expect some back reflection away from the sharp edges. So these are some of the benefits, at least in terms of robustness, let's say, which is a term thrown around quite a lot. Also, the manner in which they're built, they are guaranteed to exist, and this is reliant upon the underlying principles that are associated with these invariants. That are associated with these invariants. And also the design is fairly generic for these symmetry generated states. What that means is what you'll see throughout this presentation, examples for photonics. We started acoustics experiments, water waves. For most scalar systems and for even vectorial ones, you could use similar or the same principles. So I hope that this motivates why we're interested in them. So just a very brief overview in terms of this. How are these generated? We start off with a degeneracy at this K point here. So we start off with a degeneracy at a K point, and because we're not breaking time reversal symmetry, there will be another degeneracy at a related K point. So this is the time reversal pair of this K. Now we have both of these points. They're both identical in every which way. They have the same eigensolutions, degenerate eigensolutions, but something happens. So for example, with the earlier case of a triangle and a hexagon, if we rotate that triangle to the left, let's say that's plus alpha here. And if we rotate it to the right, that's minus alpha here. We end up with an identical band gap for both, and it's simultaneous, i.e. they occur over the same frequency range. However, the actual properties around these valleys that demarcate these band gaps are actually different. And I'll go into that a bit more later. But it's the actual properties of these valleys. So to differentiate the difference between the valleys of the media, which when rotated to the left, for example, a triangle and a hexagon, and the triangle rotated to the right, that leads to these edge states. And then what we end up in panel C are with two edge states. There's a blue edge state and a red edge state. And each of these generally, at least in the hexagonal case, pertain to two geometrically distinct modes, C and D. So we can clearly see that the actual modal pattern of one is distinct from another. So this is just to give you an overview of what we will be doing. And then I'll go into more detail now. So there's not that much maths in this presentation. I wanted to keep it light and picture heavy to make it more digestible. But the equation we'll be dealing with is the Kirchhoff-Love equation here. It's a fourth order equation. We have, if beta x is constant, we have a biharmonic operator here. On the right-hand side, the f of x, those are forcing terms. Our forcing terms in this instance, we'll use a mass-loaded plate. And the masses will be characterized by this MNP. Your psi n kappa are your displacements for band n, and for wave vector kappa. Omega kappa are your frequencies. And these delta forcing terms are for point-like constraints. So we will have points at the locations, sorry, bad control of this. But XNP will be the locations of our point constraints, and they will each have masses governed by this MN term. So this is, a, I guess, inhomogeneous wave problem. But and the benefit of this model is that we end up with Fourier series representation, which makes it very convenient and quick to compute. And other examples are shown in these other papers. We could use small but finite Dirichlet scatterers or even Neumann scatterers, and these will also yield closed form solutions. So the point being made here is we could use this elastic plate equation. I'll show some experiments that we've done using this plate equation, but they can also be transposed to other idealized regimes where we use Dirichlet or Neumann conditions, which can pertain to electromagnetism or acoustics. Okay, so we start off with our cellular structure, and we start off with what we have here, IV. So let me see, if I draw a line here, we have one reflectional line, and this reflectional symmetry yields the Dirac cone shown and highlighted here. This is our unperturbed cell. And this is actually for Neumann inclusions. So we end up having the symmetry protected Dirac cone here. The Brillouin zone is shown here in panel II. So what we'll do is by rotating these sets of inclusions to the right or to the left, this will induce a gap here. And in terms of this structure, it possesses a reflectional symmetry and threefold rotational symmetry, because in effect, this structure, we end up having, let me see if this works. This is effectively a triangle, basically. So let me see if this works. Bear with me. So we end up having a triangle here. So when we rotate our triangle either to the right or to the left, we will break this reflectional symmetry there by gapping it. Now for completion, and in one of the papers that we've written, we have proven by first principles that this is not the only structure that you can have. So the structure that we showed in the previous one was a C3V structure. And in terms of this structure, this has threefold symmetry, and the V signifies the reflectional symmetry. And there are two other types of structures. You can either have C6V, sixfold rotation and reflectional, or C6. And if it falls outside of these, then the Dirac cone will be gapped, essentially. So what is the mechanism? This is a pretty busy slide. So by rotating the internal set of inclusions as we've done here, we've rotated them to the left, for example, or to the right, depending upon your perspective. We end up with the diagram like this. Here I've overplotted the Brillouin zone. What that means is we have K here, and then we have K prime here. And I've decided to plot this because K and K prime are different. So here, this is your Brillouin zone as well. So you have K here, and you'll have K prime actually in this spot here. You'll have K prime here. You'll have K prime here as well. Now, ordinarily we'd just plot this, but what you have here is you have a red spot and a blue spot. And in those red spots and blue spots, we have the following eigensolutions. So for the red spot, we have this eigensolution. Can you see my cursor? Or not? Okay. So for the red spots, we have this eigensolution here. And the blue is a mark of the chirality. It's like a pseudo spin, and it's calculated from this formula here with the F. So this kind of shows this angular momentum flux that you have. And if you see here at these particular corners, it's rotating anti-clockwise. Whilst for the blue, it's rotating clockwise. Not only that, if you look at the displacements, the actual inner product of them, is zero. They're effectively orthogonal. So what happens here? At the K point, we have red over blue, and at the K prime point, we have blue over red. And this is associated with, these are associated with a topological quantity known as the value chair number. So here, for the red, we would have the signum of this quantity be plus, and for blue, let's see the green. Okay. For the blue, it would be minus. So we would have minus here, we'd have plus here, we'd have plus here, that's the signum, and minus here. Sorry. Okay, so I'm just figuring out the controls here, sorry. So what this value will show here is if we drew a line which comes from here across here, then what we would end up with is, so let me make it clearer. So if we drew a line from here across to here, we would end up with the picture that we see here. And what the colors signify here is this thing known as the, I guess you could call it the chirality quality factor. So red would be a direction that's favored, red would be a direction that's favored like, so red would pertain to, let's see, red would pertain to something which goes in one direction, and the blue would be in the other one. I can't reduce the thickness of these lines anyway. And this one would be going this way. So the red would be going in one direction and the blue would be going in the other. And then what happens is if we take this line and we compute it for the lower region, we see that this rotation shifts. And what this means is at this valley, it's the opposite of this valley. And this is also what the colors indicate. So ultimately, I guess what I want you to take away from this slide is the red is associated with this particular quantity that has, say, a plus value, and the blue has the other. However, since we've broken or perturbed the structure, these valleys or these regions, KK prime, that were formerly the same are no longer the same. And it's this relationship and their relationship to the pseudo spin that actually yields these edge states. So ultimately, so ultimately, I guess that's it. So now what happens and how do we get these edge states? So if we stack, say,
excuse me, Mehul, is it okay to ask a question?
Sure.
So if you look at gamma mk in, of course, if it's just a uniform hexagonal cell, it's going to be irreducible Brillouin zone, but with the additional structure rotated inside, it's not an irreducible Brillouin zone for this kind of system. And of course, you can do the cross-sectional plot, which is absolutely fine. You can choose any contour you like, but it's not the irreducible Brillouin zone for this case. So, in a sense, the question is, if you look at the full three-dimensional dispersion diagram, do you see any special features that say may bring some interesting effects? What should you say?
Perhaps, but in terms of this, so I admit, so when if you rotate the inclusions like this, in terms of spatial symmetries, your Brillouin zone would be something along like this, right? It would be this triangle, which would be a sixth of the Brillouin zone. However, what people often forget is in Fourier space, you also have time reversal symmetry, and what that actually relates is that would relate your kappa to minus kappa, which will allow for further folding. So this plus region is actually related to this region by time reversal symmetry. So what that means is something which has angular momentum flux spinning to the right here. If I reverse time, it's spinning to the left here. So you can actually reduce your Brillouin zone down to this. If you solely use spatial symmetries, I admit it's only a 6th, but if you incorporate time reversal in Fourier space, then it is a 12th again.
But
So
have you looked at the, I mean, you should be able to see it from the full 3-dimensional dispersion diagram. Did you have a look at it?
No, I mean, I've seen them in other papers, but I may have plotted them a while ago, but I have not had a look at them recently, I
Okay.
can say. But
sorry for the interruption.
Yeah.
Apologies.
No problem. So yeah, I guess this is the heart of the talk, in a way. I mean, if you understand this, then I hope you can carry on through to the rest of the talk. So we take a region and we take one rotated. So this one is the triangle rotated to the left, and this one's the internal triangle rotated to the right. So if we stack one medium over another, then we end up with these modes which rotate to the right, and we end up with these modes which rotate to the left. And these effectively have an interface that runs through the middle. Now, if you just think of, I don't know, if you think of two cogs, if any of you have ever seen newspapers being made, this is the way I think of it. Then this one rotating to the right and this rotating to the left would actually mean that you have something coming along in this direction. And that's the essence, I think, of ultimately what's going on. Now, in terms of actually showing this rigorously, because you introduce an interface that breaks the symmetries, at least in the vertical direction, in the Z direction, there is actually a problem to be done here, perhaps using matched asymptotic expansions. So in the internal region, you'll have something going on which takes you from one medium to the other. But on the outer region, it would start to resemble the bulk media with some kind of envelope modulation. So for example, this is how you get these edge states. So I put one left rotated medium above a right one, and I end up with these edge modes that you see here. There's one which is a smile, which is a green, and there's a frown, which is a purple. Now, this green pertains to red over blue, which is right rotated medium over left rotated medium. And this blue over red is when you have a left rotated medium over a right rotated medium. And because they are constructed in geometrically distinct ways, you end up with these two edge modes that we were showing before. Yeah, there's a point. Okay, cool. You end up with two edge modes which are geometrically distinct. A natural question to ask is, how is this related to our bulk diagram? So the bulk diagram we had before is this one. And when we go along this path that we're actually doing here is we're doing something which is actually a 6, but we're actually going to gamma, to K prime, to M, which is here, back to here, back to here. But ultimately, what we see are these points here. And when we take, let me move this away, when we make a cut of our medium, we actually cut it, for example, along this line here. And what's important is we have these K prime points, which are different from our K points. And we want these K prime points, which have a particular designated pseudospin, i.e. to the left or to the right, to project onto the same region. So this one will be projected here, and then the same K prime point will be projected here. K would be here, and then the other K will be here. So we end up with two spots effectively. We end up with two spots. We end up with, let me get rid of it. We end up with something here, and then something here. So when we go from a two-dimensional structure to the one-dimensional one, we end up with these two spots here, which is exactly where your crossing points are, here and here. So this is how the projection happens. And what's important is, for our bulk structure, at a fixed frequency, so along here, we are projecting on to a point of the same chirality or pseudospin. So if I cut it along here, then this point here, the red, will be projecting onto the red point here, as we see from here in the cut. So that, I guess that's the most salient point. You need to have a designated pseudospin that's independent. So that's how you get these edge modes. Now, a natural question to ask here is, how do these bulk modes properly relate to these edge states? And there have been bulk boundary correspondence that have been written in some of these papers that I've highlighted here that relate the bulk and the bulk modes to the edge modes. And naturally, there's other, as I increase the perturbations, as this band gap increases, your edge modes will reflect your bulk modes less and less. But ultimately, I guess here what I'm trying to illustrate is by stacking the media in different ways in a strategic way, you get some of the properties of your bulk media. And if you are here or here, if you are here or here, you end up with distinctive chiralities. And this is related to the chiralities that you had in your bulk, i.e. your pseudospins. So let's see this in action ultimately. No, I mean, ultimately it's like, it's all theoretical. Let's see what actually happens. So here, these were experiments done by Kun Tang and Patrick Sebar in Brillouin University. They have this structured elastic plates. Here, what you see is the underside of the plate, and you have these magnets. So what these are acting as is they're acting as point constraints, and this is the upper side of the plate. And what we wanted to see is, could we navigate energy, the flexural waves, so the outer plane, around a corner, for example, in a realistic system. And what you see here is, you see the same mechanism. We take a Dirac cone, break it, we end up with two edge states, and then we run through the computations, and we have two distinct edges for the hexagon, and they have geometrically distinct eigenmodes. So we end up with the following results. So this is for gentle bend. So it's 2 pi over 3. The angle here is 2 pi over 3, and this angle is pi over 3. So this one here, and then this one here. And these were the numerics, and these are the experiments. So firstly, just in terms of what's happening, in a lot of the experiments that we see that we aren't able to visualize the modes. But here, one thing we can see is we can see how one mode couples into another. So you can see that these left-facing modes, I don't know, that was a bad drawing, but you can see that these left-facing modes are coupling into a right one there, and these left ones are coupling into left ones. And this modal conversion can be seen from the prior band diagrams. In actuality, when we get this, we can still visualize the modes, but naturally there's quite a bit of loss here. And the loss actually stems from the fact that there's a lot of coupling between the modes in the plate with the air either side of it. So it's quite lossy. So this is one negative, which is kind of obvious, which is, okay, so these principles and these ideas are generic across wave systems, but naturally we have to specify it for each particular wave system in order to optimize it. So that's the cost of creating, like, I guess, generic concepts. We were thinking of shrinking this down and putting it into a vacuum, but we decided against it. But still, one thing that you can see from this experiment, you can see the modal conversions here and the lack of modal conversion here. So just prior to this, we were talking about hexagonal structures, but similar principles can be used for other geometries. And here we show it for squares as well. So here what we have, our geometry is this one here. So we have a square inside a square. And this square has the most important symmetries are these vertical and horizontal ones. So the horizontal one going along here, and the vertical one going along here. That's barely a straight line, but you get the message. And then by rotating these inclusions, we can break both of these symmetries. So in a similar way to what we did before, we start off with two degeneracies. We start off with one here and one here. And by rotating this internal square inclusion, we create this band gap here. And when we do that and we project it down onto either the horizontal line or the vertical line, we end up with band structure which looks like this. And here we have two gapless edge states. One is related to an even mode along the interface. It's blue here and it's red either side. And here's your anti-symmetric mode. And I'll briefly show some experiments that Muammer and his team at Femto have done or using water waves. And here's their experimental setup. So there's a lot of information on this slide as well, but I just wanted to give a pictorial representation. Okay, we have hexagons, we have squares. What are the crucial differences? And why would we bother using the squares if we have the hexagons and vice versa? Well, what we see here, the most important information is actually in the interfaces. So if we have two zigzag hexagonal interfaces, I hope that you can see that one interface here, i.e. blue over orange, is distinct from the orange over blue. For the hexagonal case, we have two distinct interfaces. And what this shows itself as is when we obtain these edge modes that we had before, we had the concave and convex ones, or the smiley and the frown. We have a smiley which exists along one of the interfaces, and this even one exists along the other. And here's a representation. Here's your odd one, or here's your even one, i.e. this excitation along the interface. Whilst for the square, different to this, we obtain orange over blue and blue over orange. But however, the cool thing here is that this interface is related to this interface, i.e. a right propagating mode here is like a left propagating mode here. We don't have any such relationship for these interfaces. So what does that actually afford us? What freedom does that afford us? That's an interesting, to me, that's an interesting question to ask. And in terms of the edge states, once again, we end up with a smiley and we end up with a frown. However, because of the relationship between the interfaces, i.e. orange over blue and blue over orange, both of these edge states exist along, inverted commas, the same interface because they're effectively identical. The reason why they don't couple into each other is because one is an even mode and one is an odd mode, which is what we see here. So the key differences between the hexagon and the square model that we have here is here you have two edge states. Each edge state belongs to a distinct interface. Here we have two edge states which are orthogonal, which belong effectively to the same interface. Now, where and why does it make a difference? Well, it would make a difference in a hypothetical scenario if we were making multi-structure domain. For example, this. Our edge state, the K vertex, does not couple very well to the edge state at the K prime vertex. And I'll go into this a bit more later. They have limited overlap integral and they're pseudo-orthogonal, but they're dependent upon the perturbation parameter. So what this means is, if I have a forward propagating state, it won't so easily couple to the state going to the backwards propagating state. So if incoming mode, this incoming mode is actually at the K valley. And this couples to two other K valley modes, but it won't go along the straight line interface. And the reason for that, effectively, is we have this mode coupling to itself. And then if it wants to propagate along to this K prime one, it has to couple to this other mode here, which is not only even, but it's not only is it even, but there's also a wave vector mismatch. So it cannot couple to the mode coming along here very easily. For the square, you actually alleviate this issue because what you have is you have an incoming K mode here. And as you go from blue over orange to orange over blue, this curve effectively stays the same because a right propagating mode here is effectively a left propagating mode. A right propagating mode here is actually a left propagating mode here. The same also is true. If you wanted to go to the right here, it is coupling to the left here. So what you end up having is the incoming mode is this one here. But as it goes through this nodal region, this curve flips. So you end up with something like this. And you end up having K here. Sorry, you end up having, you're right, it's K. You end up having, what's wrong? You end up having K prime here, and you end up having K here. So effectively what happens is this incoming mode, which is at K, pointer. So this incoming mode, which is at K, the mode that exists here is effectively the same curve, but flipped. So it ends up coupling to a mode which has the same chirality, but which has the same chirality and same group velocity. And the reason is because it's effectively coupling to the same interface. Whilst for the hexagon, it's not. You're trying to couple odd into even. So what we end up generating there is this three-way energy splitter. And this was done for plates. And as we showed very earlier on, either side of the interface, you have right here, left here. You end up seeing a similar behavior here. So for exit 1, we end up having it going one way. We end up having predominantly going the other way. And the same is true for exit 2 and exit 3 as well. And all of this is done in your regions when you rotate this one to the left, this one to the right, this one to the right, this one to the left. So ultimately, I guess the point I'm trying to put across here is that you can engineer different behaviors intelligently by tailoring the geometry. The majority of people use the hexagon for particular reasons, but the square will also afford you additional functionality. Now, hypothetically, let's say we wanted to break time reversal symmetry, you would still not be able to partition the energy 3 ways. It would still be 2 ways, which is what we see here. And because the concepts are fairly generic, they can map over to other systems. So it's not just true for structural elastic plates. Here's an optical 3-way beam splitter. Something else that this design affords is you can actually make it go around a pi/2 bend, which you can't do with the hexagon, while still maintaining some of the principles of these pseudo spins and robustness. So here are some experimental results that were done by Muema and his team, and this was done for a highly dispersive system. The numerics are shown in panel B and E, and the actual experiments are shown in panel C and F. And you can see a fairly tight confinement of these modes. And we did this for different widths. So I thought this was a fairly remarkable result considering that we're dealing with water waves here, shallow water waves. There is an issue, there's one potential issue here, which is the presence of the diagonal symmetry. So for the square, you have this diagonal symmetry. What this ends up is you end up having this Dirac cone here, and when you rotate it, you're breaking all 3 reflectional symmetries. Now this Dirac cone here is not on the periphery of the Brillouin zone, it's along the diagonal. So even when you rotate it, you still end up with gapless dispersion curves that relate to these. It's still allowable, but there are means to optimize this design, which I'll discuss a bit later. So even though these are the general principles, I don't think that any of these can be useful until you've optimized the design with certain quantifiers. So a way to remove this diagonal symmetry, if I have a square and a square, I have that diagonal symmetry. If I have a rectangle, I would not. Another way is if I have, for example, an eye in here, you no longer have the diagonal symmetry, but you still have both reflectionals symmetries. That's barely a straight line, but yeah. You still have both reflectional symmetries, and the same is true here, and you get rid of the diagonal. So these are mechanisms you can do to optimize the structure. Okay, so what are the general principles? So like, I've probably given quite a lot of information to those that are not familiar with these states. Some of these principles were taken from a paper we did, some were taken from a paper by the one highlighted in this archive. So first and foremost, the Dirac cones need to be well separated in Fourier space. This is the benefit of the hexagonal model. What this means is we take this line along here, which was a cut. This relates to the zigzag interface. So when we have a zigzag interface for the hexagon, we have something like this, and that relates to this line. Now the benefit that you have with this is you have a K prime point and you have a K point at the vertex. They're very well separated. Whilst for the square, they are here, they're along what we would call the high symmetry line. So they're not at the high symmetry points, which they are for here. So this is a benefit of the hexagonal model, for example. A nuance here is for the square model. You can actually tailor the material parameters to move these points out, and this would increase the Fourier separation. The actual separation of the points and what you get will increase the separation of the edge states, i.e. the forward propagating one and the backwards propagating one. And this is also related to the allowable degree of disorder. So the further they are, the shorter the range of disorder that you can have within your system. Another important point connected to the above is that the smaller the wavelength, the better, i.e. the smaller the wavelength of your edge state, the better. This is related to, I guess, Fabry-Perot resonators, where for maximal transmission, you want a finite number of wavelengths connected in one lead. So let's say we want to go around a bend. We have this straight line here. Okay, that's red, bad color. Disappeared. We have a straight line here. Then we want it to go around here, for example. Once again, maybe white, gray. Now, if we hit this corner point here with maximum amplitude, then we don't have great transmission ultimately. We don't have great transmission around this, around the bend. However, if we hit it with minimum amplitude, then we have very good transmission. Now, if you can increase the Fourier separation, larger wave vector, smaller wavelength, better transmission, ultimately. For the square case, you end up having a beating envelope modulation, and the reason for that is we end up having a curve like this, which is closer to your gamma point than say like a hexagonal one, which would be something like this. So this is a benefit of those. Other principles. This is an optimization problem in a way. So smaller the perturbation, this will inhibit backscattering more. However, there'll be more leakage. So if you have a domain wall here, smaller the perturbation, you'll have something like this, but there'll be limited backscattering. Larger one, naturally, you'd have something like this, or be very localized, but you'd have greater backscattering. So it's ultimately an optimization problem. And a way to see this in a quantity to use here, that was plotted in this paper, is the Berry curvature. So you have, for this green case, you have, for the green case, you have very localized Berry curvatures here. And what this means is your pseudo spins at the two different locations are very localized. Now, if I perturb it more, then what you start to see is you start to see this slope, and you're starting to see more of that leak into the other region. So what this means is you're starting to see these pseudo spins for which our system is reliant upon. You're starting to see the mix, which isn't good when it comes to backscattering. So in a way, this is an optimization problem. I want a small perturbation, but at the same time, I don't want too much leakage perpendicular to the interface. Another important principle is you want the transition across your domain wall to be as smooth as possible. So in this paper, they use Schrodinger's equation, and the domain was chosen to be a smooth tangent function. And they did this so they could explore it analytically. So what you see here is, I hope you can see it, is if you slightly break it, you get one single localized mode here, which is this little red dot. And what they did in these lower panels, this one and this one, is they followed that red dot. What happens here in the y-axis as I increase the perturbation? Your x-axis here is the energy, i.e. your frequency or whatever. So what happens is here is a case where your domain wall is a tangent function with no disorder. So as you increase the perturbation, i.e. the rotation of your medium or whatever, this mode persists. The red one is a mode that's generated using these principles from topological physics. And this blue one is a trivial mode. So basically a bandgap mode. Now, when I introduce disorder, this bandgap mode, this topologically trivial bandgap mode disappears, but this one persists. Now, it may change its frequency, but it still exists when I introduce a certain amount of disorder. So That's one of the better ways that I've seen to actually visualize this. So I guess the four main principles are: you want the Dirac cones to be well separated in Fourier space, smaller the wavelength, better. Smaller perturbation will inhibit backscattering more, but lead to greater leakage into the bulk. And you want the transition across your domain wall to be smooth. Other cases that are highlighted, the relationship between the domain walls. So as you showed before for the square case, for the hexagon, whether you're blue over red, red over blue, what is their relationship? That will actually lead to different types of behavior. And another important point is when we had these regions that were associated with plus and minus sigma and Berry curvature value Chern numbers, you want them to project onto regions which have the same. So what I mean by that is we have, if I drew a horizontal line here, then this one, this plus projects onto the same plus here, this minus projects into the same minus here, and the same is true here, as was showed before, with the K prime projecting onto the same K prime here. Now, what happens if you don't do that? So before with the hexagon, we had a zigzag termination. If we had an armchair termination, which is this Y1 we see here, then we end up with edge states which look like this. And what you see here is you see a gap between your two edge states, and this is known as band repulsion, and it can occur when you have two edge states which are not orthogonal. This is a popular model that's used, done by Wu and Hu, where you have these hexagonal cases and you expand and you shrink them. But what you see here is in the fairly similar behavior to what you see in the armchair termination. You see a gap that forms in between them. And what this means is you actually have an admixing of your pseudo-spin states. So you don't have this angular momentum, this specific angular momentum either side of the interface. And a cool way to actually see that was done in this ACS photonics paper, where if you have a source on one side of the interface, which has a preferential angular momentum direction, so this one's to the left, then you would expect the mode to travel to the right, which it does here. But however, if you change the position of the source, it couples to another mode and it goes to the left. So what this is effectively saying is there's an admixing of your pseudo-spin states. If it's a truly kind of symmetry generated topological mode, you should be able to change the source position on one side of the interface and it should always go in the same direction. So as I was saying before, where can we use these ultimately? So you saw a fairly kind of lossy elastic plate model. So I guess if these are going to find uses, they're going to be in areas in which you don't want a mechanism that's too intrusive. So you want something that's passive, simple, and efficient. So one idea is in photonic crystal fibers, and I worked on this problem alongside Sebastian. And conventional photonic crystal fiber has a localized mode in the middle where you introduce a cavity. But these topological ones, you can have certain designs and localized patterns, such as this let's say St. George's cross here, or this triangle or hexagon. So effectively what happens is if you have this triangle along here, we'd end up with like a Toblerone shape here. And Sebastian, I don't know if you want to mention anything more about these.
So I just wanted to mention that, and this might be of interest for Sasha, we've been looking also at this kind of light and sound interplay in topological photonic crystal fibers. So you can have some kind of crosstalk between various types of waves in these fibers. I find this really exciting, Sasha, don't you?
Yeah, it's nice. But here you don't see the directional preference in the context of chirality, but certainly localization. Yes, localization is great.
Yeah.
I guess the heart of it, I guess you could see that if we did the angular momentum flux, but that's more in the paper than it's here. I guess in terms of here, it was with photonic crystal fibers, we want a highly localized mode. This is another means to get it. Maybe it could be a some. So yeah, another avenue potentially is for some form of energy harvesting. So this was work done alongside Bogdan and Sebastian. So if we change the actual thickness of, let's say, a plate, what happens is as you change the thickness in your infinite medium, what happens is your edge state modes, if we just took our smiley, for example, it would move upwards. So here your frequency isn't changing. We place a source to the left side. And so this orange line is not changing, but this is just an illustration. Your curve is moving upwards. Your orange line is fixed. And as your curve moves upwards, it starts to get close to the standing wave frequency, which is here. And as it gets close to the standing wave frequency, which is there, your envelope modulation decreases. And also your wave becomes almost static or quasi-static. So what you start off with here is you end up with fast envelope modulation, and then you end up with an almost standing wave pulse here. So by engineering either side of the domain wall, these geometrical kind of waveguides, we can also use it to localize energy in a particular location. Another illustration of this, for example, is if we start off with an increased frequency. So what does that mean? If we start off with a higher frequency, it would actually mean, for example, this case here that I'm pointing to right now is this case here. It almost localizes instantaneously. But as I increase the frequency, this one goes here, it localizes further and further to the right. And here, it goes through all three steps to localize almost to where we saw it here. So perhaps this could be used as a way to localize energy in particular regions. A few potential future directions. I think I've spoken long enough. Something I've been looking at more recently is neural networks. So here what you would have is you'd have particular inputs and you'd have outputs and you want to optimize it. This has been used a lot in image recognition, for example. I had a MATLAB code that I want to run live, but I'm afraid I'll destroy the system. But ultimately, it's what you see when you have any image recognition. If any of you ever use Facebook or anything, and it automatically tags you. So what it does is it will look at it'll get enough data of your face, and then it would effectively interpolate, and then it would train this algorithm. So it outputs, you give it your X, it gives lots of my pictures of my face. And then it says, this is Mehul, this is Mehul, this is not Mehul. And that's your information that you have. And then next time it sees a picture that it hasn't seen before, it gives you with a certain probability, is this Mehul, is this not Mehul? And if it's above a certain threshold, then it tags me in the picture. Now, how is this related to anything that I've just said? Well, I showed a handful of principles here. I would say these four are the most important. So potentially what you could do is you could inversely design your waveguide based upon these principles. I could feed it, for example, I could feed it the Fourier separation. I could feed it the wavelength. I could feed it the perturbation, the localization length, the transition, what's the transition across the domain wall. And with that, it will output a particular structure. And you could have, say, transmission past for a particular kind of disorder. So if I wanted to optimize that transition, then what I would do is I would send it lots of Fourier separation, this property, and then the structure that is used to get me those quantities. And then I would ask it, okay, I want this kind of Fourier separation, this kind of thing, which is related to this kind of transmission. What geometry is the optimal geometry for that? So maybe this can be used, or these methods can be used for the inverse design of these symmetry generated topological states. Also, quasi-periodic structures, they have enhanced localization, Anderson localization. Could they be coupled with the localized edge states? And then also moving a lot of this, especially the more theoretical components, to high dimensional structures, i.e. 3D and surface waves. And this was taken from another paper. And you can see quite nice localizations in these 3D structures. So I think I've been over an hour, give or take. So let me see. No, okay. Let me just try. Let me see this, sorry. Yeah, I've asked a polling question. So that's pretty much the end of the talk. Please be honest. The answers are anonymous. And a few people and a few people that really helped out with this stuff. This was a massive team effort. There are many contributors, and they're labeled here. And the research was funded by the EPSRC Leverhulme Trust Research Fellowship, Multi-Wave Technologies. So yeah, I guess my hope here was just to relay some of the concepts in a more kind of superficial manner and try to organize them, because this is a fairly vast field and there's a lot of crosstalk, a lot of different things being said, but fairly few papers that are actually cohesively bringing things together. Many unanswered questions. I think the biggest one is, can we truly quantify what we're doing, the efficiency of it, what's actually going on, as opposed to just, I guess, stretching it further and doing new physics. But that's my philosophy. Anyway, thanks for listening, I hope.
So let us thank our first webinar speaker. I think it would be good to have some questions from people. So you can raise your hand and ask your question.
Thank you, Mehul. I wanted to say this, that if you wanna have some questions, you can raise your hand. You have this option. Just write your name in the participants list. So you're more than welcome.
Nobody said bad yet, but I think they're being polite. It's 3 okays. Okay.
Okay,
So,
Younes.
yeah. Okay.
There you go. I'm showing the poll results now. There you go.
So yes, Younes.
Yes. Do you hear me?
Yes.
Yep.
Okay. I have a question for you, Mehul. Thanks for the presentation. That was really clear. I just want, sorry for that. If you get back to the slide regarding the energy harvesting.
Sure. Sorry, let me just. Yeah. Yeah.
This is a time-dependent analysis.
No, this is not a time-dependent analysis. I should hand it over. I'll hand it over to Bogdan, who did a lot of the computations in this.
So this is time harmonics.
Yeah, time harmonics. Yes.
Okay, so the localization in each picture. So you are changing the motif, the manufacturer, depending on the position. That's it.
No, it's the height of the plate.
It's between the
yeah. Sorry,
the frequency. The frequency.
That's the frequency. It's not the height of the plate. So the height of the plate is the same, but your initialization frequency is different.
That's wrong.
Okay. And did you try to see, for example, the quality factor for these? Localizations, because if you can, for example, put some defects, punctual defects or something like this, and see if we have a high quality factor, because here you are targeting the energy harvesting, but we can see as well the case of sensing.
Yeah, so I think that's a really good question, because in terms of these topological modes, they allow for a certain amount of disorder. So just to recap the question, they allow for a certain amount of disorder. How impervious are these localized patches to those disorder points? Well, naturally, the question to ask there is how do we properly quantify the disorder when there is no grading? And then subsequently, at least numerically, how would we do it here? We haven't done that analysis, but I think that's a good question. Bogdan or Sebastian, do you have anything else to add?
Okay, and a second and final question. When you have the bending guided guides, is there any problem of impedance mismatch? Because when we have something like very severe as trying to change directions, So I don't know. Probably at the edge, can we quantify the impedance mismatch? Because if we send a time-dependent analysis wave at the edge, you will have a lot of reflection depending on the angle of bending. So can we have any to quantify this?
I guess the best way, I mean, okay, so firstly, just a slight digression. In terms of the angle of these, for these states, because they're geometrically engineered, you can only have certain angles, meaning for the hexagon, you can have, this is a bit tangential, but you can only have 2 pi over 3, and then you can have pi over 3 here. For the square, you can only have a right angle, so that you're fixed to the type of angled bends that you can have. But the actual angled bends that you have are related to the dispersion curves that you end up getting. And then it's all about the coupling. And when it comes to the coupling, it's just, I would just do, to be honest, I don't exactly know the answer, but I would just do a frequency sweep and transmission and just see. But what I would do first is actually just try to, in order to optimize the bend, because these edge states are related to the bulk, I would try to start off with the bulk principles. So I would try to, look at the Berry curvature first. I would examine the transmission across the domain wall when I introduce an interface. So the bulk properties would be the perturbation, the localization of the Berry curvature. This is also a bulk property. How far apart are my direct cones? That would lead to different lambdas. And then the transition across the domain wall is the domain wall. So using those 4 quantities, let's say, then I presume, I haven't done this fully, this is a lot of work, we should be able to either increase or decrease the transmission around a bend. But I don't know how well that answers your question. I would use these quantifiers of the bulk to increase or decrease or tailor the transmission around sharp interfaces, sharp bends.
Okay, thank you.
Any other questions? I could do a poll. Any other questions? Sebastian?
No, I just want to add that effectively this time-dependent problem is a very interesting study on itself. Younes is perfectly right. I mean, it's something which should be addressed at some point. And I think it's been partially addressed by the fact that the experiments done by Patrick Seba, if I'm not mistaken, are in the time domain.
Yes, I believe they were, yeah.
So you could see already that you have a lot of scattering. You have a lot of back scattering. I think you can see this in the snapshot.
I mean, there were back scattering, but the major source of loss in those actual experiments was to do with the actual air either side of the plate. Yeah, I don't know, Murma, would you like to comment on these experimental results a bit more that you got for water waves? Is Murma around?
Oops.
I think he's muted. That's anyway. So yeah, I mean,
but
Murma.
perhaps.
Murma.
No, I don't know. You don't hear.
Okay.
Yeah, probably a way to do this, Mehul, is just to, for example, because this can be due to the impedance mismatch, and I guess if the impedance mismatch is just the rate of difference in propagation of waves. So if we see, for example, the dispersion curves, we can try to search for a frequency in which we have the same slot. So in this case, we can try to engineer if we take this condition, so there will be, I guess, very much low backscattering. I don't know. This is just an idea. I don't know
Sure.
how
I guess
can we.
okay. What do you mean slot? I don't understand.
In fact, if you take the Brillouin zone, and depending if you are rotating in a way and in another, so we can see, for example, there are almost flat bands in the band gap due to degeneracy lifting. So your bands are almost flat. That's why we have localizations, and I guess even if we want to try to transmit a lot of waves, energy inside these it will take time to do this because of these flat bands. So even with these flat bands, we can see, for example, if in a direction and another, if we zoom and we see if there is they have almost the same slots, even if they are again they are
you're talking about actually matching. Oh no, in terms of the flat, where were the flat bands? I've lost the presenter thing here, so I think Wormer's now the presenter, so I can't change slides. But where were the flat bands? I guess.
You're the presenter again.
Okay, good. Sorry, where were the?
No, if you take, for example, just to take any dispersion curve.
Sure.
Where you have, for example, before and after turning the.
You mean the turning point, so the standing wave?
Yes.
Sure. I mean,
take
ideally, in terms of these modes, I think you want to be like. I mean, the folklore here is you want to be at the intersection between the smiley and the frown. So there you're at least for the hexagon, you're far away from the gamma point. So you're away from the standing wave. So it is moving. The only time where I was espousing like we want to be close to the flat portion, i.e. the zero group velocity, was for the case of, for example, energy localization or energy harvesting. And that's in order to slow down the wave. But there are actually pros and cons to this as well, which are more in the details, which are in the archive preprint. Ultimately, we want to be around here or somewhere around here. And I guess if you match the slopes a bit more, then sure, I guess there would be perhaps better coupling there. But I guess the biggest thing with these modes is it's not easy to couple from here to here. It's actually less easy than for a cavity waveguide mode. That's the main point.
And when you are talking about direct cones, to me, direct cones should be at the highest point symmetry points. So you are using this term in a normal band crossing. Is it? Can you correct me about this?
I mean, what I class as a direct cone, or what I think most people class as a direct cone, is any linear crossing between bands. I guess what you're referring to is, for example, with the hexagon, you have direct cones which are located at the vertices. And the reason why people use hexagons is because these are symmetry induced, i.e. they are guaranteed to be there. You're not sure which frequency. As long as you are in one of these symmetry groups, you're guaranteed to have a direct cone. So if your structure is one of these, you're guaranteed to have it. There are 17 different space groups in 2D. And it's only for the hexagon that you're guaranteed these. Why? I showed the square. So you can actually engineer direct cones. So for the square case, for rectangles, you can strategically engineer direct cones. And they can occur, or crossings. And they can occur along high symmetry lines. But as far as I know, and as far as I can tell, even by proofs and other group theoretic applied to like wave physics books, you cannot push these out to the vertices. You can only get them at that. So the vertices are your high symmetry points, and these lines are your high symmetry lines. So you can actually engineer direct cones along the high symmetry lines for almost any 2D structure. But you can only really get them at high symmetry points for the hexagon. But they're all classed, I mean, linear crossings, they all come with this non-zero value Chern number or non-zero Berry curvature. So that's what.
But also I guess one of the conditions is to have 3 bands and not 2 bands. No.
If you have 3 bands, I believe it. Like I haven't looked into this myself, but I believe it would actually change that topological quantity. But I haven't looked at it myself. So I think if you have like a direct light cone is a linear crossing with a quadratic. So
the third band, if you have a third band, I think the problem is that the third band doesn't have a linear crossing with the other 2. I think it comes, almost flat. You see what I mean?
You're thinking of like when you have a quadratic local curvature, so it would be something like a inflection point or through the crossing.
Yeah, something like that. Yeah, but
okay.
So yeah.
Okay, sounds clear, Mehul. Thank you.
Okay, no problem.
I think perhaps Younes, you were thinking of this kind of Dirac cone cloaking papers. No?
Yeah, sure.
In which case they have actually using the third one.
A very good presentation performed by Siti Chan in YouTube. If you just and he explained very good this kind of Dirac cones and symmetries, etc.
I mean he's done a lot to do with like these different types of degeneracies and other things. I think I guess what I'm interested in the future is like this has already started to be done. I just wonder if it's been done in a kind of strategic and organized way, but looking at different types of degeneracies for 3-dimensional structures. I think a lot has been done, but I'm not familiar enough with the literature. So effectively, the philosophy here was, if we can understand the 2-dimensional structure to the best of our knowledge, then we basically upgrade it by 1-dimensional to 3 dimensions. And as this other group did, perhaps we can start to engineer the most efficient types of these states and not just showing these states.
Okay.
So yeah.
So maybe we call this an end. So let us see our speaker again, and I would like to mention that next week our second webinar speaker should be Marco Mignacci. So
yes, that's right.
Give a talk on mechanical metamaterials, I believe. And he told me he will mention a bit also topological properties of mechanical metamaterials. Right? Any more questions? Just to, perhaps even propose a webinar speaker for the future. No?
I mean, I would actually like there's certain scientists that I would like. So there's somebody called Tetsuyoki Ochaya who's in Japan. I've never met him, but I quite like his papers. And I think these webinars are good. I mean, a lot of us know each other, but I don't know him. I like his papers, and he's far away, so it'll be tough. I guess people who fall within that remit, i.e., they're geographically far away, we don't really know them that well. This would be a way to engage them and get to know them. So someone like him might be good. I personally would like him.
Excellent proposal. Let's go ahead and send him an invitation. So it should be for this autumn, I guess, because we are fully booked until August. I'm pleased to say. You can have a look at our diary. Bogdan.
Okay, guys, thank you, Mehul, once again. Very nice talk, and we are pleased to have you. Yeah, let's meet next week for the next webinar. Thank you all.
Thanks for the invite, and hope you guys have a good day.
Bye.
Thank you.
And in the meantime, do not. Okay, okay, too late.